So today we're going to look at a technique I used in my short film Deep Rooted, where you can rip a ground terrain apart using cracks generated from a set of input curves. Let's get started. So let's start by going to a Geometry Nodes workspace. We can use the default cube because we're going to generate our own geometry anyway. We'll go through that process quite quickly. Let's create a new node graph. I'm going to start with a quadrilateral. Give ourselves a little bit of scale. 10 meters should be enough. Plug that into our output. Okay, so we want to fill this in with some nice evenly spaced triangulated geometry. Fill curve. Then we can distribute some points on that face. We'll use Poisson disk to get a nice even distribution, and we'll just ensure there's a certain amount of distance in between the points. Probably push the density up nice and high, because the amount of points will always be constrained by this minimum distance. Start to bring this down until we get a density we like, maybe something like that. And then we want to instance on those points a very small curve object. And the only reason for this is so that when we ultimately fill our curve, we've got some interior points that will generate that triangulated topology for us. So we make a curved line, extremely small, something like this, instance on the points, and then if we realize those instances into actual geometry, join them with the quadrilateral and then add a fill curve at the end, we should get some nice evenly spaced out topology. And you see at the edges we're getting some very nasty long thin triangles, and that's because the resolution of our quadrilateral is not enough. We need some extra points on that boundary edge. So if we subdivide curve, you can see as we start to add some subdivisions, the points along those edges will even themselves out. And also we probably don't want our points to go right up to the edge. So if we do a scale elements here, scale faces, and just bring this down a tad, we can just push them away from the boundaries a little bit. There we go, that's going to do us. Okay, let's add some height variation to our terrain. Using a noise texture, we'll subtract 0.5, multiply this, and use that to offset the position of our points in, not the X, the Z. So let's reduce the scale of this a little bit, and then we can increase our multiplier. I'm going to go even smaller on that. There we go. Just so that our terrain's not completely flat. Okay, let's put this into a frame, Control J, F2 to label the frame, and we'll call this terrain geo. Now, we're going to need some curves in order to represent where we want this geometry to crack. So let's add a Bezier curve. Go into edit mode and just scale up these points so that they are beyond the boundaries of our terrain geometry. And then, just so that we don't start off making life too easy for ourselves, we try and anticipate some of the complexity that we might encounter further down the line. We're going to duplicate this curve, go into edit mode, and then just rotate so that we're dealing with multiple curves at once. Let's add these to a collection, new collection, call it cracks, and then if we go back to our initial cube, we can drag the cracks collection in here, and that's going to give us a reference to our curves. These come in as instances when you bring in a collection node, so we want to realize those, and we're going to want to ensure they snap onto our terrain. So we're going to need a little bit of extra resolution, because at the moment these curves have only got vertices at the start and the end and no information in between. So I'm going to resample by length, 0.1 meters should be fine, and then we are going to want to set the position of those curve points. So using our terrain output, drop down a raycast node, and we want to offset our source position. So we'll take the existing position of our curve points, we're going to add, say, 50 meters in the z-axis to it, and use that as our source position, just so that we can ensure all the points start above the terrain. We only want to set positions on points which register a hit. So I plop that into the selection, and the new position is going to be whatever the hit position is. So we drop that into here, and let's have a quick look at our curves just to make sure. Yeah, they are now following the ups and downs of our terrain, and any points that overshoot are not being affected. Let's add these to a frame. Again, give it a label. So we'll do curves to terrain. Okay, so our next job is we want to sample a path through this triangulated geometry that best represents our curves. The way we can do that is using the shortest path nodes. We're going to loop through each curve in our source collection, treat each one separately for now. So we'll use the new for each element zone. I'm using Blender 4.3 here, so as long as you're on at least that version or later, you'll have access to this for each element zone. And what this will do, if we plug our cracks collection in as the source geometry, change this to spline, whatever nodes we execute within this zone will be run for each spline in this source geometry. At the moment we've got 2, so this is going to run twice. So within here we want to sample the curve at a factor of 0, so that effectively the start of the curve, and we want to do the same for the end of the curve, so a factor of 1. We want to get the index of the point which is nearest to the start of this curve and the end of this curve. So if we get our terrain geometry and do a sample nearest, and the value that we want out of these sample curve nodes are going to be an integer, which is the index of the nearest point to factor 0 of this curve. And we're going to want the same for factor 1. Now let's grab a shortest edge paths node, and the end vertex, where we want the path to end up, is going to be the index that we've sampled at factor 1 of our crack curve. If that equals the index of the point, that is where we want our end vertex to be. So let's pipe our next vertex index through a edge paths to curves node. We want our terrain geometry as the mesh. Sorry, this should go to next vertex index, not start vertices. So our start vertex is going to be the same process as our end vertex, but using this factor 0 sample curve. So if we duplicate these nodes up and instead plug this value in, that is going to become our start vertex for our path. That's going to become our output geometry for the for each element zone. And if we now view this, you can see that we've got something happening, but it's not really following the shape of the curve. Now, to force it to more closely align to the shape of these input curves, we're going to need to associate an edge cost with these shortest path nodes. And we want to say that the closer to these curves you are as a point, the cheaper your edge cost is going to be. And that should force these paths to retain the shape of the input curves more closely. And what we're going to do is convert our input curves to a mesh, so curve to mesh. We need to generate some faces, so we will use a very short curve line here as the profile curve. And the reason we need some faces is so that we can use a geometry proximity. So this is going to give us the closest position on our input curves to our current point. And if we take the distance and plug that into our edge cost, you can see that these curves now snap much closer to the original source curves. So to make this just a tiny bit more interesting, we can also add a little bit of noise into this so that we generate a little bit more detail in our paths. So let's drop down a noise texture and scale this down a bit, and then we can multiply the factor to give us control over how much effect this has on our curves. And then if we subtract this value from our distance and just clamp that so that it doesn't go below 0. If we use this now as our edge cost, we should see that we start to get a nice sort of meandering path. The more we scale the influence of our noise, the more sort of interesting shapes we're going to get. Okay, so next we're going to need the ability to have these cracks travel through our geometry. That's pretty simple. We can do that with a trim curve node. And if we manipulate this end slider, see that our paths are traveling through the geometry. So at this point, let's add a group input and a couple of parameters just to control these from the modifier panel. Hit N for the side panel, and we want a new input. It's going to be a float, default of 1, minimum 0, maximum 1, single value. Set this to 1 on the modifier, and then we can use that as our value for the trim curve end. Next job is going to be to take our original terrain and split its edges according to these newly generated paths. So let's take our geometry, split edges. Now how do we decide which edges we want to split? Well, if we say only split edges where the distance between the edge and this path is 0, we should just get edges that correspond to these paths. Because these paths come from the original topology, there should be a corresponding edge on the original geometry. So let's convert these trimmed curves to a mesh. Let's use our old trick with the very small curved line as the profile, and then we can get the proximity, and we only want edges where that proximity is 0. So distance is equal to 0. If we use this as the boolean for our selection on our split edges, let's just view this in a viewer. We should see that now we're just selecting the edges that correspond to those paths. Okay, so next let's look at how we can start to displace our terrain geometry away from these cracks. We're going to use a repeat zone, and again we'll be just treating one of the crack curves at a time. So we're going to pipe in our geometry with its newly split edges, and the number of iterations we want to perform is going to be equal to the number of curves in our source cracks collection. So if we run this through a domain size set to curve, it will give us the number of splines, and that's going to be our number of iterations. Okay, so within here we want to separate the source cracks into a single crack per iteration. Let's take our curve geometry in as a new input. Just rename this on the repeat zone so that we know what we're dealing with. And then we'll use a separate geometry. We want to separate splines, and we want the spline whose index matches the current iteration. So if we do index equals iteration, use that as our selection, we should just get the spline that we're interested in. So if we take the selection, run it through yet another curve to mesh with the tiny profile curve, duplicate this one, we can generate a proximity to this individual curve, and we're going to use that to drive how far away from the crack the geometry is actually displaced. So if we put down a set position, we can offset and we can see it's working, but we want to use this distance as a multiplier for whatever offset we end up putting in here. So if we just put down a vector math, set it to scale, and use this as our scale. Let's just, for now, we'll put 1 in the Z component, and we'll apply this to our offset. And you can see that everywhere that's close to the curve is not getting affected, so that's not what we want. Let's map range, and we'll go from 0 to 1, yeah, so 1 meter away from the curve is where the effect will stop. Let's reverse these, and now we can see that this becomes a height value that we can use. And one more thing we need to do before this will work properly is make sure that our curves objects are actually getting piped through to the output of the repeat zone. So if we drag this through, you'll see that now we're getting a ridge per curve and the edge is not being affected. Let's just reroute these a little bit so that they're not cutting through our nodes. And now you can see we have control over how much this gets displaced and how far from the curves the displacement happens. Okay, so let's try and figure out how we decide which direction to displace our geometry, because at the moment it's just going straight up in the air, but we want it to actually push away from the curves as the cracks open up, and we're going to need to figure out the curve normal in order to achieve that. So we need to know the normal of the curve at its nearest point to each of our corresponding terrain points. So if we use a sample curve node, this is going to need a factor input. So to figure out the factor that's nearest to our points, I'm going to need to capture some information before we turn this curve to a mesh. So let's just make a little bit of room, and I'm going to drop down a capture attribute node here, and let's capture the spline parameter as a factor. And then once we've turned the curve to a mesh, we can use a sample nearest surface node, and then we'll grab this factor that we captured as our value. And now we can plug the output of that into our sample curve node as the factor, so that we're now sampling the curve at its closest point to each of our corresponding terrain points. We get the normal as a default parameter from this node, so we can plug that into our vector for our displacement. And what we should see now, well, this won't work at the moment, obviously, because I've not plugged in the curves to the sample curve node. So we want our captured attribute curves to go into there. And now we see that we are pushing the geometry perpendicular to the curves. The only problem is we're pushing both sides of the geometry in the same direction. So we need to figure out which side of the curve our points are on, and based on that we can reverse this displacement as needed. Let's unhook this offset from our set position just for a minute. If we drop down a position node and then blur this attribute slightly and plug that into the position of our set position node, what we see is that these islands shrink away from the curve, and we can use that as a source position to compare and get whether or not we're on one side of the curve or the other. So let's take this blurred attribute and subtract from it the position of our closest point on our curve from this geometry proximity. Let's just take that out of the set position for a minute so we don't explode everything. So let's normalize this vector. We want the dot product between the vector from our blurred position to the curve and the normal of the curve itself, which we already have down here. And if we take the sine and have a look at that, we're only looking at one curve at a time because we're in a repeat zone. But we can see that all the points on one side of the curve are getting a positive value and the ones on the opposite side are getting a negative value. So if we use this as a multiplier to scale our displacement vector again, we should find, that's a bit too much distance, we should find that we're now almost getting the results we want. We are getting some cracks opening up. There's just one or two areas where it's still problematic, and we should be able to fix that by just blurring this initial comparison position slightly more. Let's give this a few more iterations. Let's go for 10 to be on the safe side, and we should see now that that solves all those problems. And if we test with our trim curves parameter, you can see now that we've got the cracks flowing nicely and opening up as they go. Okay, so we've just been scaling this displacement vector by our different parameters as we go, and we're going to continue to do that in order to have the crack get wider as it ages, if you like. So it starts out narrow as our cracks travel through and gradually widens. So if you remember, we sampled the factor from this capture attribute node of our closest point to our curves, and we can use that straight away. If we drop another one of these scales down on our displacement vector, we should be able to use this factor value. We'll run it through a map range, and we want when the factor is 1, i.e. the very end of our curve, we want the displacement scale to be 0, and we want the beginning of our curve to get the full amount of displacement. If we plug that into this new scale, we should see that the cracks are now 0 width at the sort of leading point as it travels through, and they get wider as we go. And the toMin parameter will control the maximum width that crack is allowed to grow to. So that's probably worth putting on a group input while we're here as a parameter. And while we're at it, let's give this parameter a slightly better name as well. Call this crack progress, and then we'll add another float input called max width. That can have a default of 1, minimum of 0, maximum whatever 10, and we'll plug that into our toMin. Now we have a control here that states how wide our cracks are allowed to become. You see that dodgy effect we're getting there as our crack progress approaches 0. That's just because when the curves are trimmed right down to 0, there's no longer any curve geometry to compare anything against. So what we probably want to do is just add a minimum, a very small value to that parameter, and that should solve that problem for us. Right, cool, we're getting close to being done with this. Let's just add a little bit of vertical displacement along the crack as well. Just adds to the effect a little bit, I think, of the ground getting pushed up as it goes out, as though there's something underneath that's causing this crack and displacing the ground upwards as well as away. So let's add to our displacement vector, and we want to add some amount of Z displacement to it. We'll use the geometry proximity again, the distance. Run this through another map range, and then we want to reverse the outputs so that points closest to the curve with a distance of 0 get the maximum effect. So 1, 0, run this through a float curve node, and this will allow us to give some shape to our vertical displacement. And then one more multiply at the end of here will allow us to control the strength. Let's combine this using the Z input, and this becomes our vector that we want to add. And straight away you can see that we're now getting some vertical displacement along those curves. It's probably a bit too much at the moment. You can also push this negative to get the effect of like a river carving out a valley through your geometry. But I'm going to go for a positive value on this one. And then your map range here will control, again, the spread of how far away from curves that vertical displacement travels. You can keep it really tight so just the adjacent edges get pushed up if you want. And then the last thing we need to do is add some thickness. So simplest way to do that is just to add a solidify modifier after your geometry nodes. Give it some thickness, and then we do shade auto smooth on this mesh. Ignore sharpness, angle of about 60 seems to work. That's pretty cool. Okay, so let's have a look at this in a material preview node with a little bit of ambient occlusion going on. We can play with our crack progress parameter. It's all working good. Control how wide these cracks are able to get. And then obviously at any point you can go back to these Bezier curves, move those around, and you'll get different configurations of crack happening. Okay, that's it. Hope you enjoyed that video. Hope you learned something. I'll see you in the next one. Bye.